This is looking at the behaviour of sine x, cos x and tan x near the origin, and work on questions that show your understanding of this. Now essentially we're looking at things of this nature, sine x, at what happens when the angle approaches 0 to these things. Okay, so sine x is the one we'll be using the most. The one we'll be using in the same way will be this one as well. So I'm going to get straight to the explanation because I feel like it might take a bit of time, but we'll go with it now. So this is just from your formula sheet, okay? And in it you've got the area of a triangle rule and the area of a sector. Now sector is a pizza, a triangle, I hope you know what it is, okay? So what we're going to do is that I'm going to calculate the area of these three triangles. So that triangle, that sector there, and this triangle. So not three triangles, so that's wrong. Two triangles, a circle, and a sector. Alright? Sector is a pizza slice. Alright, so we're going to calculate those three things. Now, let's get on to it. Alright? What is the length from the origin to the edge? So this length here. Hopefully you know that that's just the radius. So that means this bit is the radius up to here as well. So you can see that I'm doing that as well. So if I use my area of a triangle rule, which is this one just here, my A and B are both the radius. Okay. So I'm going to go half r squared, because A times B, R times R. And it goes sine, and our angle is what? X. Alright. Now, that you can visually see that that is smaller than the sector. Alright, so I'm going to use an inequality. So that's going to be less than the area of a sector. So simply we've got the area of a sector, it's got radius and everything, and our angle here is just x. So let's go with that. So that's going to be less than half r squared x, so we're just replacing the theta with an x. Alright, now that is also smaller than this big triangle here. Now I'm going to take a few steps to explain the area of it. Now the area of a normal triangle is just half times base times height. Now in this one the base is r and the height is BC. It's just this length here. Okay. So I need to get that in terms of something else. So bear with me. I'm going to move this down a bit. I'm going to use my knowledge of tan. Tan x is going to be BC over R, because you know how tan is just opposite over adjacent. So that's all I've done. Alright. So tan x is just that. Now I will use this, so I'm going to change colours. That means that BC, so this guy here, is equal to R tan x. Alright. Now, what's the area of that triangle then? So the area will be half, our base is what? It's R, times our height, and our height is just BC, and we've got BC in terms of this. So it's going to be R tan x, so that equals half times R squared tan x. Now we can clearly see that that triangle is bigger, so I can put this over here, half R squared tan x. Alright. Now what I'm going to do is I'm going to play around with this blue inequality here now. Now all the blue inequality is describing what is happening with these three geometric figures. So your two triangles and the sector. Alright. So I'm just going to play around with it, and I'm going to divide everything by half r squared. So if I take, and you notice that every one of these has a half r squared, so we're going to get rid of it. So we're going to get sine x is less than x, which is less than tan x. All right. Now, for the purpose of what we're doing here, I'm going to change tan x to its original form. So I'm going to go sine x is less than x, which is less than sine x over cos x. All right, so I'm just changing it. Now, what I'm going to do is one more thing. I'm going to divide everything now by sine x. So if I divide sine x by sine x, I'm going to get 1. This is going to be x over sine x. And this will be 1 over cos x. Now, if you're screaming at me and saying that this is the same as sec x, you are completely right. But we don't need to do this for this example. It might be easier just to keep it as cos x, 1 over cos x, because what we're going to do. Now, what we need to do is that we are interested, I'm going to rub all this working out that I've done here out. What we need to do is that we want to find out what happens in the limit as x approaches 0. So when we talk about x, we're talking about these guys, all right? So we're going to find the limit as that approaches 0, all right? So we're going to have to do a limit to every single section of our inequality. So I'm going to do that real quickly. So limit as x approaches 0 to 1, change to my pen, and I'm going to write this again as x approaches 0 sine x. And now the limit as x approaches 0 to this thing over here. Okay. Now, I'm going to draw a line, give myself space, because I'm going to work under here now. Now, for this first one, the limit as x approaches 0 to 1, it doesn't affect it. So it's just going to stay as 1. All right. Now, I'm going to keep that as a limit. I'm not going to deal with that yet because this is actually what we're coming up to. I'm going to explain what I'm talking about here. All right. And what happens as the limit approaches 0? Well, we know with cos, if I draw the graph, where does it start? It starts at 1. So as x approaches 0, it actually becomes 1. 1 over 1 is just 1. All right. If you don't get what I'm doing, please ask me because it's important that we understand this. Now, this is interesting. Now, this is called squeeze law. All right. What's happening is that this thing in here is in between, is greater than 1, but less than 1. All right. Now, we're talking about a specific case. It's when the limit approaches 0. So we're only talking about really, 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 really small angles. Okay. So as the limit approaches 0, we can say because of this, therefore, as the limit of x approaches 0, this thing is approximately 1. And for all intents and purposes, it is 1. Okay. Now, if you go through the same process, I'm going to move that up there. If you go through the same process, you'll find this also, that the limit as x approaches 0, this is the case. The same thing happens to tan. So I wouldn't mind for you guys to have a go at seeing that. Make that a tan by dividing everything by cos, and you can see where we're going with this. Now I'm going to rub off the rest of the bit here. Okay. So that gives us these really interesting dynamic, and that's the basis of this whole exercise that we're going to be doing. Now, what's also true is that the limit as x approaches 0 is the same as if we have it this way around, is still approximately equal to 1, because remember, 1 over 1 is the same thing. So we can flip them over, but I'm just writing down. And also true is that as the angle gets really small, tan x over x is approximately equal to 1. So essentially we're writing the same thing as we've written here, and here we're writing it here and here. Alright, so that's the explanation of how this works. How do these questions look like? Well, let's go over here. Well, find the limit as that approaches 0. Well, that essentially just equals 1. Alright, so that was simply from here, by per definition, you're going to get that. Now, you won't get that question in your HSC exam. You're going to get something like this or even levels higher. Okay, so I'm going to show you how to write it down so you get full marks. Now, notice one thing here is that this angle is the same as this number here. It's really important. Okay, so I need to always convert before I can substitute x equals 0 into my function. I need to change the other thing, so in this case the denominator, to 3x. Alright, so now I know that my angle is the same as the denominator, so I know that bit equals 1. But that's actually not a true statement, because I've just put the 3x in there. So what I have to do is I have to put 3 here over 1, or you don't have to put over 1, because if I cancel this and this, I'm left with back with the original thing over there. But I'm not going to write that down. Okay, so I've got that. So therefore, because this angle is the same as this angle, I can go 1 times 3, and that equals 1. Now, all this working out is critically important. If you learn something from this lesson, is that you need to show all this working out. You need to put limit in, you need to match the angle at the bottom, and then a compensation fraction there. Alright? Then you need to write this line of working out, and then finally this. Alright? And it's only when we've done this compensation that we can get rid of the limit, and then finally our answer. So don't skip any steps. This is really important. All right, let's do this. So what I'm going to do is I can't change the angle, so I'm going to do the other side where I'm going to match it. Limit as x approaches 0, sine half x. I can't really change that angle, so I'm going to change this. All right, but I need to multiply it by something to make it true. All right. Now, how do I get that to equal 2? Well, I can just go 4 over 1. All right, because, and you can do it even here, 4 times a half equals 2. All right, so you can cross that out, and you'll get to the same result. So that equals 1 times 4, which equals 4. All right, so make sure you show all your working out. Make sure that it makes total sense. All right, so it's just like what we did over here, that we tried to get it back to the original. All right, what about this one? Well, this one's interesting because it's an identity. Now, I know that this identity, sine 2x is equal to 2 sine x cos x. All right. So what that tells me is that this angle is double these angles. All right. So I'm going to use that identity to change this. Now, it isn't quite that yet. All right. So I need to change it by multiplying, putting a 2 there. But what I do to the top of the fraction, I must do to the bottom of the fraction. So I get this. Over 8x. So all I've done, I haven't done no maths except I've just multiplied the top and the bottom by 2. Now I'm going to use this identity. Alright, now notice carefully. This angle is twice as big as these angles. So I'm going to make those angles bigger. So I'm going to go limit as x approaches 0. Notice that I'm still writing limit. And I'm going to go sine 4x over 8x. Now this is good because it's got me into this kind of form, which I've done over here. So that means that I'm going to write limit again. Keep writing limit until we've sorted it out. Sine 4x over 4x. Now I need to multiply by something to make it true. In this case, I'm going to multiply it by a half. All right, because 4x times 2 equals 8x, so I need to multiply it by the bottom thing over here. And now what I've done is I've matched the angle to the denominator, or it could be vice versa because you're going to get the other version as well. So now I'll write my beautiful working out. So that means that this thing is 1. So I'm going to show that in my working out. 1 times a half, so the answer is obviously a half. All right. Now that's the end of these examples. Just a couple of notes, and these are really, really important. It is what happens in the exams, we have brain farts and we forget things. Now these are just angles, all right? All of these are just angles. If there's a sine there or a tan there or something, they're all just angles. So if we forget what they approximate to, although it's not that hard, we can just put it in our calculator, all right? So, for example, if I got this thing and I forgot totally how to do it, okay, I can make sure that my calculator is in radians, all right? And I'm going to put something really, really small. So maybe 0 with, what's that, 6 zeros, all right? And I'm going to pop them into there. Maybe save this into my memory so I can do it. And the calculator will give me something very close to my answer. Obviously, the more zeros you put in, your calculator will eventually approximate to and give you the exact answer. Now, with that in mind, you can, with the answer there, you can trace back and hopefully that triggers some memory for you. Or the other way that this can help you is just to validate that you got the right answer. Anyway, I hope that makes sense. Peace out.